All right. This is the last method of integration that we're going to learn, so you can celebrate it. That's the last method. The whole next chapter, which is our last chapter leading up to the AP exam, will be applications of the integral. So here we go. Partial fractions and the logistic equation. We're going to derive the logistic equation today. I'm going to teach you the method of partial fractions. And then we're going to use the logistic equation. So the derivation I do of it, we'll only do that once. So you can, as you're going through it, I'd just like you to follow through it, take notes on it, make sure you understand the process. But the practice problems I'm going to have you do will be a little simpler than that. So I'm just going to ask you to take the logistic equation and use it, apply it. So to write a rational function as a sum of partial fractions depends on the degree of the numerator being less than that of the denominator. So if you're going to use the method of partial fractions, we need the degree of the numerator to be less than that of the denominator. Now we've seen that in u substitution as well, but what's going to happen on these problems is if you let the bottom equal u, its derivative will not be at the top. So that will lead you to go, okay, I've got to use another method. Also, we must know the factors of the denominator. In other words, we must be able to write it as what we call linear factors, like x plus 3 or 3x minus 2 or just x. Those are all linear factors because their degree is 1. So I decided to insert into this section, this is not partial fractions here, in example 1. I'll let you copy down example 1 there. With the integral of x squared over x squared plus 1. This is a representative problem of anything where the degree of the numerator is the same or bigger than the degree of the denominator. This is a method you can use on those. Okay. So if the degree of the numerator is the same as or bigger than the numerator, and I have a couple of problems on your homework like this, we're going to use long division. Long division to rewrite it. And it works like this. Take x squared, and we're going to divide it into, we should probably put our placeholders here, 0x plus 0 if you want. We're going to divide it into x squared plus 0x plus 1. Turns out we're not, it doesn't really matter here on these, but we have our placeholders. Reminds that this placeholder is going to make a difference right here. But x squared divides into x squared 1 time, so we just write a 1 up here. And then we multiply the 1 by this polynomial. It's x squared plus 0x plus 0. Put a line underneath that and subtract. Remember doing this? How come I'm not using synthetic division on this? Do you remember why? Yeah. So if I subtract, I have 1 minus 0. This is just 1. So I end up with a remainder of 1. Now, 6th grade, it was okay to write R1. But that's not going to help us in rewriting this fraction. What does this mean, remainder of 1? 1 over 1 over x squared plus 1. And we'll just, yeah. That means 1 over x squared plus 1. That's right. So I can rewrite my integral here, which is x squared over x squared plus 1 dx, as the integral of 1 plus 1 over x squared plus 1 dx. So I'm taking my original problem and I'm rewriting it. And that rewrite gives me 2 pieces that I can't find the integral of. That's kind of the goal in here. Anytime this is what I talked about earlier, everything you knew about simplification, remember simplification is bringing it all together, and it's reverse in integration for the most part. So we're going to separate these out into 2 terms that we can find the integral of. So you want to think of it as integral of 1 dx plus integral of dx over x squared plus 1. So what's the integral of the left-hand side? or the left term here, I should say. Just x. X plus c, and we'll put the plus c at the end here. Do you recognize the second one on here? It's not as easily recognized sometimes. Not an ln form, why not? Yeah, that power is the wrong power, yeah. It's not a u substitution. What's that? No, that's not going to work. Good thought, but if we move this to the top, we have x squared plus 1 to the negative 1. If I integrate that, I land at a 0 power. That's a problem. Yeah, that's kind of what keys us into ln, but this is not ln because it's not x to the first. You're right on that. It's also not a u substitution because I would need to have a 2x or x at least on the top. Yes, inverse trig. Ah, I got it. It is. Inverse trig. Which one? It seems like we notice it's inverse trig when it's a fraction with a square root on the bottom, but this one we don't notice as easily. Inverse trig. So it's just the inverse tangent one, remember, is 1 over a. What is a in this case? 1. So it's just going to be 1 here. Inverse tangent of u over a. What is u? X. And I can skip doing any kind of u substitution because a is 1, u is x, and the derivative of u would simply be dx, so it makes no sense to do u substitution. It'd be like just swapping variables out. Okay, so you got to see this as direct application of the formula. That's probably the one that would show up, on the AP exam is the inverse trig one, so we want to be able to recognize that. I haven't seen the inverse secant one show up, but inverse tangent would probably be the one that would show up. Seems to be. That's it. So that's using long division. So just keep that example in mind. And when do we use long division? Yeah, same or greater. Yeah, equal or greater. So let's look at the method for today. This is the method of partial fractions. This is when the power on top is smaller than the power on the bottom. And the bottom can be factored. So we have if f of x equals p of x over q of x. I wrote these notes before I had math type or something on this smartboard, but this is p of x over q of x, where p and q are polynomials with degree of p less than the degree of q. Do you know what that statement means? Okay with that. Degree of p, that means degree of the top fraction, which is 1, is less than the degree of q, which is the bottom fraction, or 2. So the degree is the highest exponent on that polynomial when it's written in descending order of the powers. And if q of x can be written as a product of distinct linear factors. What are distinct linear factors? Yeah, like x plus 2. What's that?
Functions for lines.
Yeah. They're expressions that if the y equals that expression, it would be a line. Yes. Distinct linear factors. Distinct meaning, different ones here. They could be just distinct in terms of their power. We have distinct linear factors. We have 2 distinct linear factors here. Then f of x can be written as a sum of rational functions with distinct linear denominators. You can actually apply this method to fractions that are like, if I factored it and I had, say, an x plus 3 quantity squared, you would treat that as one factor, and then x plus 3 to the first would be a separate one. So this method can be applied to denominators which have many factors. We're just going to keep it pretty simple here. Because for each factor you have on the bottom, you're going to introduce a new letter into our system of equations. So here we're going to have 2 distinct linear factors, so we'll have an a and a b to solve for. So that's going to relate to what, this goes back and relates to matrix algebra or to what you did in Algebra 1, systems of equations by elimination, remember that, substitution. So if you have only 2 factors, you'll have a system of 2 equations with 2 unknowns. If I have 3 factors down here, I have 3 equations and 3 unknowns. Now maybe we should use a matrix to do it. And if you have any more than 3 factors down here, then you definitely want to use matrix algebra to solve. So it kind of moves into another course if we make it too complicated, but we'll just keep it simple here. I just wanted you to know that you can apply this method to something with more than just two factors. So my first step is to rewrite 5x minus 3 over x squared minus 2x minus 3. We're going to rewrite it as two separate fractions, so pull it apart. So first of all, I should factor the bottom. Factors is x minus 3 times x plus 1. My first step. And my next step is to say, okay, maybe I'll do it like this. Let me erase this original. Move this over. That'll be enough room right there. So we're going to rewrite that factored form of the original as a over x minus 3 plus b over x plus 1. That's just saying that I understand that there is an a and a b. Something exists, a and b, such that if I found a common denominator here, I would end up with this, which would end up being this. Okay. So there is an existence of an a and a b that will make those two fractions as equal to the original problem. So that's my goal. I'm going to rewrite that integrand, and then I can integrate it. So here's the process. I need to clear fractions here. So what would I do to each side to clear fractions? You remember what this is called in mathematics? Multiply the abbreviated LCD, least common denominator. Yeah. In this case, it's the least common multiple of all these factors. We call it the LCD because we're talking about fractions here in the denominator. So multiply by x minus 3, x plus 1, and I like to multiply it in factored form. Room here. And do the same thing on the other side. Put parentheses around this guy. We have x minus 3, x plus 1. It is. So I multiply each side by the least common denominator of both sides of the equation. I can clear fractions, giving me 5x minus 3 on the left. And on the right-hand side, the x minus 3's will cancel here. Right, leaving just a times x plus 1. And then on the second term, the x plus 1's cancel, leaving just b and x minus 3. So here's my plan. This is kind of like what you did with matrices last year. That if you had a matrix on the left and a matrix on the right, for them to be equal, each corresponding position in the matrix had to be equal. It's the same thing here. Yeah.
Question. So when you factor in the bottom, does it matter what order the x minus 3 and the x plus 1 are?
No, it doesn't matter what order they're in. It does matter when you go and find your a and b, because the a and b will correspond to certain factors.
Yeah. So when you put a and b, you just did order a first, then b. So what if you did x plus 1, x minus 3, and then a is over the x plus 1?
That would be fine. You just there's no problem there. It's just you got to pay attention when you go back and put the a and b in that you put it over the correct factor. So I'm going to now distribute ax plus a plus bx minus 3b equals 5x minus 3. I'm distributing. Then I'm going to group the x terms together on the right-hand side. So I have ax plus bx, and group the constants together, which are the positive a minus 3b. And that's still equal to 5x minus 3. Okay, next I'm going to rewrite the right-hand side by factoring out a common factor of x. I'm going to write the x on the right-hand side of my parentheses. And I'm left with a plus b times x plus, I'm going to just acknowledge that a minus 3b is my constant term. It has no variables attached to it. So it is my constant term on the right. And then here's where I'm going to equate coefficients. So we say equate coefficients. So the coefficient of x is 5 on the left-hand side, meaning I have the equation a plus b must equal 5. And the coefficient, or the constant term, on the left is negative 3, so a minus 3b must equal negative 3. So I'm equating the coefficients. Because if these two equations are going to be equal, then whatever a plus b, whatever combination I have here of a plus b must be equal to 5. And whatever combination I have here of a minus 3b must be equivalent to negative 3 for those equations to be equal. Yeah.
You just drop the x.
Yeah, well, the x, yeah, it's just like the x is here, the x is here, it doesn't change anything,
Yeah.
and then we got constant, constant. Now, you're going to see some problems where there's only a 1 or a dx on the top here. Let's think about this for a minute. If there's only a 1 up here, then what is my coefficient of x? If there's only a 1 up here with no x attached to it, what would the coefficient of x have to be? 0, yeah. So you got to just keep that in mind, that if that particular variable doesn't show up on the left-hand side, its coefficient was 0. And then the constant coefficient, if this was a 1, would be 1. And that'll happen quite often. You'll have a lot that'll just be dx over something factorable. All right. So using the method of your choice, you can go ahead and solve for a and b. Why don't you do that right now? And solve for a and b. You got it already? So you can use substitution or elimination, or guess and check maybe here. And we have a equals 3 and b equals 2. Quick mental check will show that that's true. Plug them in for a and b and got the right hand side. But you have to go through that process, substitution or elimination.
So I did it the opposite way.
Right, but you're still going to have the correct number over the correct factor.
Oh, okay. It's okay.
Yep. So we have in any order, right? In any order, we have a new integral. And our new integral it's the integral of, I got to go back here and look. I don't remember what a was over. A was over x minus 3. So I have 3 over x minus 3 plus 2 over x plus 1 dx. So there's my new integral. And each of those pieces I know the integral of. Hopefully you do too. You recognize them? Rewrite it here for you, one more step. So I would think of this as the integral. I could pull the 3 out front here if I wanted to, of dx over x minus 3, plus bring the 2 out in front, the integral of dx over x plus 1. Do you recognize that dx over x form? What is it? Yeah, it's ln. So we've got 3 ln of the absolute value of x minus 3 plus 2 ln of the absolute value of x plus 1 plus c. And you're going to need to leave your absolute values in there unless it's an initial value problem and you know that you can drop them. It's not going to make a difference depending on what you're plugging in for x. That's it. That's the method of partial fractions. If you look at even the table I gave you, there's a bunch of things on there that kind of look like this. ln's of a bunch of terms. That ln form shows up a lot. All right, question for you. How would this be different if my original problem had 3 factors? How would this be different here? If I had, say, a cubic on the bottom of the very original problem. So yeah, I'd have a over something plus b over something plus c over something, and then we have a system of 3 equations. Yeah. So we get ugly, we'll keep it simple. This is the process of partial fractions. We're going to use this process to derive the logistic equation. Okay. All right. Just a little bit of a summary of what we did 2 days ago, what we've been doing. We've seen that the exponential growth at the beginning, or we could call it unrestricted growth, can be modeled by the differential equation dy dt equals ky. It looks like this, where k is greater than 0. That's growth if k is greater than 0. It would be decay if k is less than 0. And we saw that it has the solution y equals c, or we said a, e to the kt. It's kind of that PERT equation. Principal times e to the rt, same form as that. So that's the exponential growth equation. We know that if we have a differential equation this form, which you'll likely see on the AP exam, its solution is an exponential equation that looks like this. But after our rumor activity, we suggested a better growth model for population in a restricted environment. And that better growth model looked like this. It's called the logistic equation. It kind of goes up, levels out in the long run. I made the statement that the limit is called the maximal capacity, and the rate of growth is fastest somewhere in here where it's making our turn, where it's steepest, and that happens to be always halfway in between the maximal value and 0. So it's always halfway in between. And then you can actually calculate that rate of growth by plugging in half of the maximal capacity into the differential equation right here. So the differential equation is k times y, m minus y. That's one form of it for the logistic growth function. And now what we're going to discover is what is y if this is the differential equation. I may have shown it to you 2 days ago, but I don't remember. I told you not to take it. So we're supposed to remember that. There's a better equation for growth that has the limiting factor in there. We're going to derive it now. So buckle up. You ready?
I'd go from KY to KY multiplier, like what's the M is the population?
M is the maximal capacity. Y is actually the population, and T is the time. So it's kind of different. I mean, this Y is corresponding to the dy up here. So Y is the dependent variable, acting kind of like an independent variable in equations we've studied in the past, right? But Y is the population, M is the maximal capacity, K is the growth rate. All right. So, don't write down the whole problem. You can just say this is 7.5. It's, I think it was page 470. I didn't write it down. Let's say it was 474, but it's in 7.5 this problem. I wouldn't write down the whole problem. I'd just like you to go through this process with me. This is another practice problem. But we have in 1985 and 1987, the Michigan Department of Natural Resources airlifted 61 moose from Algonquin Park. That sounds like fun. Ontario to Marquette County in the Upper Peninsula. It was originally hoped that the population P would reach a carrying capacity in about 25 years with a growth rate of, and they're modeling the growth rate with the differential equation. Remember, differential equations are rate of change equations. So we're modeling the growth rate with the differential equation. It's dp dt equals 0.0003 p times 1,000 minus p. And some questions that relate to what we talked about last time. What is the carrying capacity in here? The carrying capacity in this equation is the 1,000. Okay, it's the M in our equation. So jot that down. Write down the differential equation and maybe have an arrow pointing at. You don't need to have the A, B, C necessarily in here, but you should know what the carrying capacity is. It's M. The K, of course, is our K. This is our K. And actually, it's going to be that K times M that will give us our growth rate. So I may have misspoke earlier. This value right here, this is our K in the equation, which will not exactly be our growth rate. It'll be actually the M times K that is our growth rate. I don't know if you remember when we did our rumor activity, we had an M on the bottom of the equation. So this is our K. The P is our population at time T. It's the P of T. It's our population at time T. So at a specific time, say at the 20-year mark, we'd have a certain population. So that makes sense from there in terms of all the parts. Because what I'm going to ask you to do on problem 27 is not the instructions on there, which is to do what we're going to do right now together. You're going to just answer the questions with what you know about the logistic equation. So you can skip to the end. Just take the logistic equation and interpret it. So what is the carrying capacity? It's 1,000. What would be the moose population when it is growing fastest? Yes, it would be. So growing fastest is always going to be in this logistic equation model M over 2, which in this case would be 1,000 over 2 or 500. And if you know that that's where that's going to occur, I think if you look at the graph, it makes sense. If I could go back to the graph, then I'll come back to this. Graph of our logistic equation, you know, where is it steepest? It's about halfway in between 0 and M, where it ends up being steepest. I think that makes sense. I'll demonstrate it to you as well at the end when we graph our logistic equation and compare that to the differential or to the derivative of that. But it is halfway, and if I want to find out what the growth rate is at that point, what do I do with this 500 here? Yes, the 500 represents a P value, and so I'm going to plug in 500 for P. Where? Yes, both of the P's in the dp/dt equation. So you're going to take the dp/dt equation. I should have left more room here. The whole thing moves. Those are all linked together. So you take the dp/dt equation here, and it would equal 0.0003 times 500, 1,000 minus 500. Plug all that in. So 500 times 500 times 0.0003, and we get a dp/dt of 75. What are the units on that? These aren't people we're talking about. Moose per year. Yes, that is correct. That is a rate of change. So our growth rate, when it is growing fastest, is 75 moose per year. So that's something that will show up on the AP exam, just knowing if I'm calculating a growth rate and I'm already given a derivative, we just plug it into the derivative. If I'm given a certain time and I want a population, I would plug it into the original. No. Moose per year. Moose per year. It's going to be moose dp per year. The acceleration would be year squared, but all right. So I have the final part here is what they ask you to do on 27, and you get to not do this again, but just do this once with me. We're going to start with dp dt equals 0.0003p times 1,000 minus p. There it is. And first step on here is to use separation of variables. So I am doing, in the first step here, separation of variables. So I'm going to move the p times 1,000 minus p down with or below the dp, and I'm going to move the dt up with the constant k. So that's the separation of variables step. So write that down. Now, after you've separated variables, we have two distinct linear factors on the bottom here. We've got to use the method of partial fractions to figure out the a, and then we need to go over each of those factors. Okay. So I was going to give you a chance to go ahead and do that right now. So I'd like you, without showing you the answer here, starting right here, we're going to go ahead and find our a and b. All right, so hopefully you got your a and your b. We have this a integral is going to be a over p plus b over 1,000 minus p dp equals the right-hand side. I can integrate no problem. It's just a constant, so I'm going to integrate it to get 0.0003t plus, I called it c sub 1. I'm going to change out constants as I go through this. It turns out on this one, it's probably, well, it's probably better to go ahead and wait to plug in our initial value so we get it kind of in the right form first. So going through that process, we got a and b were both 0.001. And here I'm explaining that, okay, this is really a u substitution here. And so if we let u equal the 1,000 minus p, du would equal negative 1 dp, meaning I need to stick a negative 1 in here. It looks like I also, let's see, also just divided through by 0.001 is a smart thing to do here. Divide through by the 0.001. Pull it out in front and divide through. And so over on the right-hand side, I have 0.0003t plus c sub 1 divided by 0.001. And then we're going to integrate each side. So, by dividing out the 0.001, I've got the integral of 1 over p dp, and then here we have the negative 1 that we needed to add in here. We bring the negative out front here. So this ends up being minus ln of 1,000 minus p. This is what I said. You have to be careful on this integral. When you integrate dp over 1,000 minus p, it will be a negative ln of 1,000 minus p. So let me go back up here. Let's go back up here. So first thing I did was I went ahead and divided through by 0.001. Are we okay with that? Just pulling that thing out and dividing it out, and trying to get rid of some of the decimals on the left before I integrate it. And then here in green, I'm just trying to show you that when I integrate 1 over 1,000 minus p, I am going to have a negative ln there. That's what that's demonstrating. So here, the integral of 1 over p is going to be ln of p, and the integral of this thing right here is going to be negative ln of 1,000 minus p, and then equals you're dividing by 0.001. Basically, dividing by 1 over 1,000 is the same thing as multiplying by 1,000. So this is actually my growth rate after I've done that multiplication, 0.3t. And the reason I called it c sub 2 is because I've had to divide my original c sub 1 by 0.001. So it's a different constant. I called it c sub 2. So what you see in red here, it might be good to just show that step before we do the next one. This next one takes some explanation. It's an algebraic thing. It's one of those things where it's kind of equivalent to, I think when I asked you to integrate secant of x, remember I told you multiply by, a very carefully chosen one. I think it was secant x plus tangent of x over secant x plus tangent of x. I would liken this to that. I know what is supposed to happen at the end, so I'm doing some algebraic tricks to get us there. So what I'm doing in green here is I am multiplying through by -1. And the purpose for that is so that when I rewrite this difference of logarithms as a single logarithm of the quotient, I will have a single p on the bottom, not the 1,000 minus p on the bottom. And that will make it easier to solve algebraically. I'll show you in a minute. So to take my word for it here. But we're going to distribute through by -1. You might be looking at this green distribution of -1 going, why is he doing that? And it's to get the p ultimately on the bottom of the fraction. And I will show you why we want it there later on. So if you distribute through by -1, you get the expression negative ln of p plus ln of 1,000 minus p equals negative 0.3t minus c sub 2. So I'm taking the approach that I'm going to go ahead and just solve for, I think solve for p first. So the next step here is going to be what I have in red. I'm going to take and rewrite this as a single logarithm. Because I have the difference of two logs, it can be written as log of the quotient. Okay, there's remember this statement, ln of a minus ln of b equals ln of a over b. Okay, that's what I'm using to rewrite this logarithm. It's this thing over this thing. So it's 1,000 minus p over p equals negative 0.3t minus c sub 2. And then to get rid of the ln, I'm going to exponentiate each side. So if I exponentiate the left-hand side, I'm left with just 1,000 minus p over p. I dropped the absolute value because I'm plugging in for my population a positive value. There's no value of p that's going to require me to use the absolute values on this. Okay, p is between 0 and 1,000. It actually approaches 1,000. So I exponentiate each side, and then I realize that when I exponentiate the right-hand side, I can think of that as e to the negative 0.3t times e to the negative c sub 2. And e to the negative c sub 2 is just some other constant. Let's call it c sub 3 and move it out in front. Okay. So I'm just going to do that process of taking this constant that I've circled, move it out in front as a product. And then it's in the next step that I needed to have p on the bottom. See, if I have a monomial term like p on the bottom as opposed to 1,000 minus p, I can break this up as two separate fractions. I have the fraction 1,000 over p minus p over p, which is 1. So if you think of it, there's one fraction, there's the other. One fraction here, one fraction here. And so we have 1,000 over P minus P over P, which is 1, equals C sub 3 e to the negative 0.3 T. We're almost there. Remember, what was our goal? Remember what we're trying to do here? Find y equals, but in this case it's not y, it's p equals, yeah. P equals something in terms of t. So next step is we can add the 1 over to the other side here. So I have 1,000 over p equals c sub 3 e to the negative 0.3 t plus 1. So that's adding the 1 over. And then if we think about this as a proportion, so I'm putting the divided by 1 there to help us see this as a proportion, I can apply the cross product property, which says P and this c sub 3 e to the negative 0.3 t plus 1 can swap positions. So my final solution is P equals 1,000 over c sub 3 e to the negative 0.3 t plus 1. And that plus 1 is not in the power. And that's pretty much the general form of the logistic equation. This one's specific for this problem because the 1,000 would be replaced with an m. This negative 0.3 t comes from a product of k times m. And the c sub 3, they call it a in the logistic equation in your textbook. How would I find the c sub 3 for this problem? 0 comma something. Yeah, I don't remember what was the initial number of moves that we airlifted to the island? 75 was that's when it was the greatest. 61. Okay. So yeah, I probably have it written down here. There it is. T equals 0, P equals 61. So I plug in 61 for P, 0 for T, meaning this entire bottom section will become C sub 3 plus 1. So I plug in 0 for T, 61 for P, and then I've got to solve for C sub 3. So good times there, a little cross product property to get the C sub 3 up top. I would just swap the 61 with the C sub 3 plus 1, and then subtract the 1 over, and you should get 15.3 for your C sub 3. And so our equation here is P equals 1,000 over 1 plus 15.3 e to the negative 0.3 t. And that is in the general form of the logistic equation. The plus 1 is right over here. I just moved it over. I guess you could write it in either order, but this is the general form. I went ahead and commuted them so it would fit the general logistic equation, which is on the bottom here. The general logistic equation is P equals M. Remember, M is the carrying capacity, 1,000, over 1 plus A. Now, A is not quite the initial value. Remember, the initial value of moose is 61. So A is not 61, but we can solve for A by using the initial value, 0, 61. And this exponent up here is actually the product of M times K. So K is not quite the growth rate, but M times K is. And T is the time. So I thought we'd run through that once. I'm not going to make you run through it again on 27. I'd just like you to answer the questions on 27 using the logistics equation. And if I ask you to do anything with this on your exam, I will give you the logistics equation like this, and then ask you to answer some questions about it, okay? I won't make you derive it. But hopefully you can follow the process at least. You're going to do that same process on some simpler problems on here. I'd like you to actually do 20, if you don't mind doing 27 first, that'd be great. Just put this up here. So if you can answer the questions, you get to skip to the end. I'm going to give you the differential equation on 27, and I'd like you to write the logistic equation using what we know about the variables, okay? So you can skip the whole process. Yes, put it in this form just using what we learned here. And then 1 and 5 go together. On 1, they ask you just to find A and B, and on 5, they ask you to integrate it. So let's at least get those 3 done. I think you can get farther today. It's one of those days.